Welcome to lecture number 22 for ECE 476 Advanced Embedded Systems. In this lecture, we're looking at measuring current and heart rate. For example, this is the current drawn by an incandescent light bulb. And here's my heartbeat, or my pulse, as measured by a pulse sensor. So a little bit of background. This is one of the lectures from 476. These are lectures on Bison Academy. That's a website that contains many of the online courses offered at NDSU. Go to Advanced Embedded Systems. These are the lectures, homework sets, and so on for Advanced Embedded. We're currently on lecture number 22, measuring your heart rate and current. So a little background on the Raspberry Pi. The Raspberry Pi Pico has got 4 12-bit analog inputs. 3 of those are connected to the I/O pins on the Pi Pico board. Of those 3, 2 are used by the joystick for XY motion. The third one is free to use for other things, like measuring current, measuring your heart rate. The nice thing about analog inputs, analog sensors, is they're actually pretty easy to measure. I just connect power ground to them, take the analog output, tie it straight to your Raspberry Pi Pico, and I've got a reading. I can measure that with a voltmeter, I can measure that with an oscilloscope, measure that with the Pi Pico. This lecture looks at measuring current and heart rate. Current, we'll look at using a current sensing resistor, as well as an N-to-1 transformer. Then we'll look at the current draw for different types of light bulbs. We'll also look at a heart rate sensor from Amazon. So let's start out. To measure current, one of the problems is the Pi Pico can measure voltage. It can't really measure current. But using a current-controlled voltage source, also known as a resistor, I can convert current to voltage, at which point the Pi Pico can read it. Now, one of the ideas behind sensors is you're not supposed to change what you're measuring when you add the sensor. So I want to have a resistor which is small, so it doesn't really change the resistance all that much, but it needs to be large enough that I can see the voltage. That's why they build 1 ohm and 0.1 ohm resistors. You might kind of wonder, why would you ever buy a 0.1 ohm resistor? Well, this is why. From V equals IR, if I have a 0.1 ohm resistor, 1 amp gives you 0.1 volt. If I have a 1 ohm resistor, 1 amp gives you 1 volt. That converts your current to voltage. I can now do something with voltage. Well, if I do that, like with a 0.1 ohm resistor, it's not going to be a lot of voltage. If I add an amplifier, I can then create that and convert that to a larger voltage, so the A to D reading, the A to D on the Pi Pico can read it. So for example, suppose I want to have a 0.1 ohm resistor so that I don't really change how the motor operates, but I want to have a voltage where 1 volt is 1 amp. Well, right here, it'd be 1 volt, or 1 amp gives you 0.1 volts, times 10 gives you 1 volt. If I multiply by 100, I now have 100 milliamps is 1 volt. So this is kind of a current sensor. If I measure V2, I know the current I load. And 1 volt gives you 100 milliamps. That's if I can take a 0.1 ohm resistor and tie it straight to ground. Sometimes you can't do that. We don't really have to put the 0.1 ohm resistor to ground, put it anywhere in the circuit. Then using an instrumentation amplifier, I can measure the voltage difference across this 0.1 ohm resistor. The instrumentation amplifier has a gain of R1 over R2 times VA minus VB. And if you do the node equations, I know at the output, V plus equals V minus. At V plus, current left and right add to 0. At V minus, current left and right add to 0. Gives you 3 equations, 3 unknowns. Do some algebra. I get the equation for an instrumentation amplifier. By amplifying the difference between the two, in this case times 100, I get 100 milliamps gives you 1 volt, or the voltage is 10 times the current. There are other op-amps I can use. For example, this is the op-amps, the configuration for an AMP04 amplifier. Nice thing about this one is they have an offset. If I want to have the offset being 1.65 volts, just make this 1.65. Then the output is the gain times the difference plus 1.65. So that's kind of one way to do it. take a resistor, add it to the circuit, measure the voltage across the resistor. A second way is use a current sensing transformer. Now these don't work at DC because transformers don't work at DC. I need an AC signal. But if I just want to measure the AC signal, like a 60 Hertz sine wave, what's the current to a light bulb, these do work. The idea is I've got a transformer. I'll have the wires go through the core of this. There's my current, my AC current. That's going to induce a voltage across the transformer. This is really an N-to-1 transformer. It's going to convert 1 volt, or 1,000 volts, in gives you 1 volt out. Add an 80 ohm resistor to convert that to voltage. Then by measuring the voltage across these two, I've got a measurement of the current. Now the circuit for it is, here I've got my current sensing transformer, 1,000 to 1 ratio. 80 ohm resistor converts current to voltage. I now want to measure this voltage. But on the Pi Pico, it just reads 0 volts to 3.3 volts. If I tied this to ground, I'm trying to measure this signal, and the negative part doesn't work. I can't go negative. If I offset it by 1.65 volts, midband, then I can measure the AC current relative to 1.65 volts. To do that, I'm going to create a 1.65 volt reference. This is just a voltage follower. This is 3.3 volts divided by 2 gives you 1.65 volts. Voltage follower, that's my circuit ground. So everything is relative to 1.65 volts. Make this 1.65 volts. This is the voltage offset by 1.65. This is my amplifier, amplified relative to 1.65. Take this to your Pi Pico. I now have a current measurement centered at 1.65 volts. A second way to measure current. Okay, so given that, let's have some fun. Let's measure the current to a light bulb. Now, a light bulb is at 60 Hertz, so ideally, if I have a 60 Hertz sine wave, this distance right here should be 1/60th of a second, or 16 milliseconds. To get some decent data, suppose I want to read 1,000 points over 3 cycles. In that case, my sampling rate should be 20 kilohertz. Well, with the Pi Pico, I can't really do a lot between samples. So what I'm going to do is I'm just going to blindly sample 1,000 times, read 1,000 points. Once you get the points, 1,000 points, then display them. And I can see what the current looks like. I'm also going to have a couple buttons. If I hit button 14, this says, bad data set, try again. Hit button 15, it says, good data set, save to file. So what the code looks like is fairly lengthy, but this is kind of the meat of it. I'm going to start out with empty arrays of 1,000 points. I will then read all 1,000 points at 20 kilohertz. This is just kind of a fudge factor. I'm not using interrupts because they take too long. Kind of a fudge factor. What do I need to get the sampling rate to about 20 kilohertz? Once I kind of guesstimate this, I can collect the data. Once I collect the data, convert it to voltage, then display the voltage. So kind of let's see how that works. If I go to Thani, here's the current reading. I am going to start out reading in the data, 1,000 points. Once I get the 1,000 points, convert to voltage, and then plot it. So as I run this code, I'm currently taking the current reading for a light bulb that's turned off. It's upside down. So this is a light bulb that's turned off, just basically noise. Turn on the light bulb, say bad data, try again. It'll collect 1,000 data points and show you there's the current for an incandescent light bulb. Okay, let's have some fun. Let's take out an incandescent light bulb, replace it with an LED light bulb. So same procedure. I'm now using an LED light bulb, just unscrewed it, screwed it back in, lights on. throw out the data, plot it. That's the current draw for an LED light bulb. And I can do that for other different types of light bulbs. Once I get the data from the light bulb, let's find the frequency content. Well, to do that, I'm going to use the Fourier transform. So with that, I can collect some data. For example, here, I've got an incandescent light bulb. If I don't like the data, I can say try again. Collects a new set of 1,000 points. Once I'm happy, I can save to a file. So here's what the data looks like. For an incandescent light bulb, this is the voltage versus time. It should be a sine wave. Basically, incandescent light bulbs are resistors. It's not a sine wave, which kind of tells me that the power is not a pure sine wave here. It's got harmonics. So this is the frequency content, primarily at 60 Hertz, plus it's got odd harmonics. This is kind of a way to tell you the frequency content or the power quality that we're getting. I can calculate the frequency content by doing Fourier transforms. Now, Fourier transforms can be done in MATLAB. They can be done in Python. In MATLAB, what I do is, if I assume my signal's in the form of sines and cosines, where omega naught is 2 pi over the period, each of these terms can be found by doing 2 over t, the integral of x times cosine. And note that the period doesn't really affect the result. The Fourier coefficients are the same regardless of the period. So in Python, what I'm going to do is assume the period is 1, because 1's a nice number, in which case the fundamental frequency is just 2 pi. Actually, the period is n. Omega naught is 2 pi over n. When I integrate then, what I can do is just do x, add to it, or add to each term, x times cosine times dt. That's doing numerical integration. As I do that, over a period, I wind up with a and b. The magnitude then is the magnitude of a and b, or a squared plus b squared square root. That's the magnitude of each harmonic. But then plot it, I get their harmonic content. In Python, I can do that. Here's routine Fourier. When I save to a file, I'm going to open that file. And what that file looks like is, here's my data. Calculate the Fourier coefficients. We'll read in the data. Calculate the Fourier coefficients. When I'm done, do a bar chart. So if I run this code, shows me this is one cycle. Calculate the Fourier coefficients. Here's what it looks like, bar chart. Primarily the first harmonic, third, fifth, seventh, ninth, and so on. Now the harmonic content is important in terms of power quality. I want a pure first harmonic. I don't want any of these. Incandescent light bulb isn't too bad. It's basically a resistor. I should have a pretty dominant first harmonic. Well, let's try other types of light bulbs. I go with a halogen light bulb. Halogen light bulbs came out around 1980, 1990. Kind of look like this. They are much more efficient than incandescent light bulbs. These are 6% efficient. They're also resistive in nature. If I plug this in, measure the current, I get this waveform. Doing a Fourier transform, I can see the harmonics. Again, it's dominant first harmonic, 60 Hertz, plus a bunch of odd harmonics. And not a great power quality I'm getting, but that's what a halogen light bulb looks like. Well, around 1990, we switched over to CFL light bulbs. CFL light bulbs kind of look like this, the little spiral things. These are much, much better. Again, incandescent is 2% efficient. A CFL light bulb is 26% efficient. You reduced your energy demands for lighting by like 90% by switching over to CFL light bulbs. But plug in a CFL light bulb, this is what the current looks like. Again, I can measure that with the Pi Pico. But look at the frequency content. It's basically spikes, noise everywhere on the odd harmonics. What this is telling you is the CFL light bulb is actually a DC device. I want DC current from an AC source, the 60 Hz wall plug. To do that, I have an AC to DC converter. This actually is using a full wave AC to DC converter. This distance right here is 1 cycle, 1/60th of a second. I'm pulling off the plus and minus peaks. That also kind of tells you I've got a problem. The power grid is not designed for spikes. It's designed for 60 Hz. But CFL light bulbs give you spikes. This can pose problems for utilities if you had a lot of people using CFL light bulbs. But again, that's the CFL 1990s to 2000s. Well, around 2010, LED light bulbs came into fashion. This is an LED light bulb. Currently, LED light bulbs are right around 37% efficient. In theory, they can get up to 80% efficient. We're not there yet, but getting there. That is a big deal. Again, it used to be with incandescent light bulbs, they were a whopping 2% efficient. Back in the 1980s, about 30% of our energy went towards lighting. By switching over to LED lights, it's now about 5%. That's a huge amount of energy that we're saving by switching over to LED lights. The current, however, for a corncob LED light bulb, that's what the current looks like. In terms of frequency content, again, I've got a lot of odd harmonics in there. Again, the power grid is not designed for spikes in the current line. It's designed for 60 Hz sine waves. This can cause problems if a lot of people are using LED lights. This leads up to a billion-dollar question. The harmonics are causing trouble for the power utilities. We've actually done studies at that with a local utility. If we have less than 30% of the people using LED light bulbs, it's not an issue. There's enough inductance, energy stored in the inductance on the power grid. It can make up for the spikes. If you have too much demand, you get a problem. Again, the power grid is usually three-phase AC. If I have three phase lines coming in, each of these is a sine wave, 120 degrees out of phase. When I add them all together, they cancel. If I have spikes coming in, three-phase spikes, add them all together, they no longer cancel. What that means is I can burn out neutral lines if I have too many high-frequency terms. It means that I'm producing losses in the transformers. Again, transformers are designed for 60 Hz. They're not designed for 300 Hz. Hit high frequency terms in the transformers, I start increasing losses for eddy currents, hysteresis, stuff like that. So what I really want is a nice clean sine wave to the LED light bulb that's 60 Hz. I want the output to be DC. That's what drives the light bulb. How do you come up with a circuit that converts sine waves into DC so that the current draws a nice clean sine wave, the output is a nice clean DC signal at 90–95% efficiency? One way you can do that is I can have the AC drive a motor that drives a DC generator that drives the light bulb. That works. I get a nice clean sine wave in, nice clean DC signal out. The problem, however, is I'm not about to have a motor generator on every light bulb. How do I do that with electronics? Well, currently we don't know how to do that. Whoever figures it out is going to be worth billions. So, open question for you. But still, with a Pi Pico, I can measure current. Next topic. If I can measure current, I can also measure heart rate. For example, this is a heart rate sensor, similar code to from before, but instead of measuring the current to a light bulb, I'm measuring my pulse. It's coming out really clean. How do I do that? Well, first step is to get a heart rate sensor. This is a heart rate sensor from Amazon. You can get 3 of them for $16. What it does is it shines a green light out. The green light, here's your finger going over it. The green light hits your skin and reflects. The idea is when your heart beats, you get oxygenated blood to your finger. Oxygenated blood has a different absorption of green light than deoxygenated blood. each heartbeat, I get a fresh flow of oxygenated blood, which changes the reflectivity. By plotting the reflectivity, I get my pulse. That's the signal. So to operate it, it's actually pretty simple. You just have the three leads. One is your power, ground. This goes to your A to D input. And they're actually color-coded. The red one is 5 volts, black is ground, yellow is your signal. Connect the signal to your Pi Pico, collect a bunch of data, same as we did before, and you get your heart rate. In this case, if I have a heart rate of 60 beats per minute, this is 1 second. So I don't really need to speed up or really push the Pi Pico that hard. If I want to have, say, 1,000 data points over 5 seconds, that's 5 milliseconds per sample. 5 milliseconds is actually pretty easy. Note that the signal is centered at 1.65 volts. Again, this probably has a DC block, centered the signal at 1.65, and the voltage isn't real high. I'm getting about 100 millivolts peak to peak on the signal. Enough to get some data, but it's kind of noisy. I'd get a better reading if I amplified it. So to amplify it, same as we did before, create a 1.65 volt reference, take the heart rate signal, amplify it relative to 1.65 volts. There's my gain adjust. Play with that potentiometer until I get a signal which is large but not clipping. Once I get a large enough signal, I can then collect it. So here's what that looks like. I can sit there and say, don't like that signal, try again. And here I don't have my finger over it, so there's no pulse. Okay, bad reading. Try again. Okay, it's somewhat better. Try a different finger. Looks pretty good. Once you're happy, I can then save the data to a file. And what did I call the file? It's called heart rate. Okay. Then open from the Pi Pico, heart rate 2. There's the time and the voltage. That plotted out is the signal. Going to see I could use a little bit more gain. It's not really changing all that much. Actually not too bad. So what the program does is it collects 1,000 data points, the sampling rate of 2.5 milliseconds. This is using interrupts. Get it slow enough the Pi Pico can keep up. The sampling rate is 2.5 milliseconds. It then, for 1,000 data points, reads in the data, saves it. After you get 1,000 data points, then plot it. And you have a heart rate reading. So what we're able to do now is we're able to read both current and heart rate. The Pi Pico's 12-bit A to D allows you to measure analog signals. Couple that with some circuits, and you've got current readings, you've got pulse readings, or just about anything else. Basically, the Pi Pico is extremely powerful. The 12-bit A to D is very versatile. Anytime I can get a signal to an analog voltage between 0 and 3.3 volts, the Pi Pico can read it. And that's lecture number 22 for ECE 476.